std vector in C++. Probably one of the most useful tools in the entire language, and yet so much can go wrong. In this video, we're going to talk about std vector. We're going to talk about how I've seen it be used incorrectly, so to speak. Not necessarily incorrectly, and we'll get more into what I mean even by that in the first place, but there are certain things that you need to be aware of and certain ways that you might be able to improve the way that you use it. An std vector in C++ is a container type that comes with a standard template library, the library of the actual language. It's a dynamically resizable container of elements stored contiguously in memory. It's basically just like a normal array that we know and love, however, the size can change dynamically, and that's what makes it super useful and super dangerous. So why is it called vector? No idea. Some guy Alex just decided it should be, and then later regretted it. Typical stuff for C++. Now, I have made videos as part of my C++ series talking about how to use an std vector in the first place. I'll have that video linked up there. That's from like, I don't even want to know how long that video is, like 6 years old probably. Now, I do want to mention what inspired this video here was this code review that I did. This is my most recent code review of a Tetris clone that someone sent in. Someone called Adam, and around 31 minutes into the video or so, I'm talking about this function over here, which we have over here, which we will take a look at more deeply later in this video. And this is just one example of something that I see fairly often, and it's very, very easy to improve it, to just elevate it up to the next level. So that's what we're gonna talk about today. Now, speaking of elevating to the next level, you're learning, Brilliant.org, the sponsor of this video, has a 30-day free trial that you can check out to take a look at all of the courses on their platform for free. For those of you who don't know, Brilliant is an amazing website filled with lots and lots of really high quality courses on various STEM topics. If you are just getting started with programming and computer science, they're one of my most recommended resources because I really like the fact that they just teach you how to think like a programmer. Instead of getting bogged down in some specific language, that's not that important in the big picture. What you want to be able to do is think in code. You want to be able to reason like a programmer. And with their extremely fun, engaging, and interactive way of teaching, you'll quickly find that it's a super effective way to learn, and you'll actually retain and memorize this information. But then, of course, once you've learned those basics, that strong foundation, you can progress onto an actual programming language like Python, again with the same method of teaching that's super effective. And all of this also extends into their wonderful math courses, which again go all the way down to the beginner level, but then into way more advanced topics such as algebra and calculus. And as I mentioned, you can get started for free. They have a 30-day free trial that you can use, brilliant.org/the Cherno. Link will be in the description below. Just work your way through some of their courses, see if you like them, and if you do, then that link will also get you 20% off a premium annual subscription. Huge thank you to brilliant.org as always for sponsoring this video. Okay, so first off, before we get into how to actually use std vector, let's talk about what kind of like metric or criteria I'm actually using here to define what exactly is a better way to use it, what exactly is an improvement, because it's something that obviously comes with the language and people have been using it well, in whatever way fits their needs, and everything's been fine. So what on earth am I talking about when I say stop using it badly, stop using it incorrectly, and improve the way that you use it here? One word: performance. Now, std vector, and in fact the entire standard template library, is probably not something you necessarily want to use if performance is of the utmost importance. Usually, what one might do is write their own data structure that suits their needs exactly, or they can use something else that someone else has written, such as EASTL, for example. EASTL is EA's version of the standard template library that's more optimized for game development and speed and performance, especially on certain platforms back in the day. We're not gonna get into that now. That was something that I used pretty often back when I worked at EA, but now they've made it available on GitHub for anyone to use. So I'll have a link to that down in the description below. Lots of alternatives out there, but this is something that I'm personally familiar with because I used to work at EA. So the standard template library, not necessarily optimized for speed and for, say, like real-time running applications like games or game engines. But that being said, sometimes it's more than enough if you just use it in a way that prioritizes performance a little bit better, and that's what we're gonna be talking about today. So step one in the how to use std vector is don't use it. Yeah, pretty funny. But what I'm talking about is you need to ask yourself whether or not it's the right data structure for you. Now, I will say without a doubt that the simple array in programming is the most used data structure. I don't think anyone can argue with that. If you want to argue with that, take it up in the comments below. And I'm talking about any array. I'm talking about a sequence of elements of any defined or variable size that are stored contiguously in memory. And that last part, contiguously in memory, that's the importance of this data structure. Data structures are data structures. They're the way that data is structured where? In memory. And that's why memory is so critical to all of this. However, there are two specific ways that you can create an array of, let's just say, fixed size in C++, and that comes down to the two different types of memory that you can use to actually store your data, and that is the stack and the heap. std vector, its job is the heap. That I think is super important to realize. The fact that the difference between std vector and std array is not just the fact that std array is just like a normal array, meaning you create it with a fixed size and that's it. You can't change the size of it anymore. But meanwhile, vector is resizable. You can just keep adding elements to it. That's the most critical difference between the two data structures, like superficially, like at a user level. But internally, the biggest difference is the fact that std array is stored on the stack and std vector is stored on the heap. And we know, or at least we should know, that heap is slower than stack. I have a video about this as well from many years ago that I will link up there. And so what that means is that even if you could use an std vector anywhere where you could use std array, because you don't have to use the resizability aspect of it, and obviously it can store, well, any number of fixed elements or whatever that you need, you should always prioritize to use std array because it is stored in memory that is effectively faster to both allocate and use. So a good example of this is from this Tetris clone code review. If we have a look at the actual code over here, this is the colors.h URLs over here if you guys want to check this out as well. And I had a lot to say about the code in this specific file in that code review, so check it out if you're interested. But this is a perfect example. Over here, we have a function called getCellColors that returns a vector, right? And what do you think this function returns? Well, if we look at the CPP file, it returns a vector of all of these elements. Do we know how many elements there are? Yes. Do we need to heap allocate a vector of these elements every time we call this function? No. Does this even need to be a function? No, but that's a different story. This is a great example of where you should just use std array with the size of 8 because there are 8 colors over here. So this is a great example of think about whether or not you actually need to use it, because your priority should be to not use it if you can avoid it and use std array instead. Now for step 2, I guess onwards, I haven't really planned this out that well. I have this little program that I've written here in Visual Studio that demonstrates how one might use this vector. This is somewhat inspired by the code from that code review, and specifically this function over here inside the block.cpp file. And we'll probably circle back to this in the end just to give a more real world example. But over here, I've just written a little program that demonstrates some of the usages of vector as well as some incorrect things that we'll correct. So here we have a vector of data. What is data or data? I'm sorry if you guys prefer data. I say data. Sorry, I'm Australian. This is just a super basic struct. It just has one integer in it called value. It's just supposed to represent something a little bit more, complex, less trivial than just like an int if I made a vector of ints. Over here, we simply push back 5 different integers here. They're ascending from 0 to 4. And then there's this print vector function that takes in a vector, prints its size, and then all of the elements nicely. So if I just run this program as a baseline, this is the result. We got 5 elements in our vector, and here they are. So what I want to do here is take a deeper look at how memory is working here, and specifically the allocation of memory. How many allocations do we think we have here? Well, to do that, in a really easy kind of hacky way, we'll say, you can just write a function right here in this file called void operator new. We'll take in size t size, that's how much we want to allocate, and we'll just return malloc size. This overrides the new operator, which the vector will use internally to allocate memory. And of course, the benefit here is we can add some of our code. And specifically what I'm going to do is add a static int called allocation count over here, which I'll start at 0. And every time we allocate, I'll increment it. And then also for fun, I might print, the fact that we allocated X amount of bytes over here. Down here at the very end of our program, before we terminate, I'm just gonna print out how many allocations we had. So S allocation count. And now let's run this. 8 allocations. 8 allocations of memory, and yes, they are all coming from the vector class. Now here's an even cooler thing. What we can do is we can actually set a breakpoint inside this function if you want to dig deeper and see exactly what is allocating that memory. So if I put a breakpoint here and I run the program, you can see we've hit the breakpoint, and over here in our call stack, we've got some external code. If we just right click and show external code, then you can see that we're going through the std, the standard template library over here, from main into vector. And vector is going to do this thing called alloc proxy. It's just going to set up like the allocator basically for this. I'm pretty sure that only happens in debug. So let's just hit F5 again. And over here we have, sure, Emplace want it back and allocate. And I'm not going to go too deep into this, but if you want to, you can see that You can. Now, if I run this in release quickly, just to see if we get perhaps one less allocation, two less allocations, okay? 6 allocations, but still 6 allocations. You know how many we should have for this program? 1. We should have 1 allocation. So let's have a look at what went wrong. So first and foremost, this is a very easy one. Don't copy vectors, unless you need to, obviously. But if you don't copy vectors. So over here, I have the print vector function. It takes in a vector. And you can see that there's no ampersand to be found nowhere in sight. So you need to add an ampersand, and this is, we're only reading here anyway, obviously, so we'll add a const reference here. And what that means is that we're not going to be copying the entirety of the vector and making a brand new one, copying in all of the elements just to print them here for no reason. We can just use this original vector and reference it. So with that, we're down to 5 allocations. This same concept, by the way, doesn't just apply to when you feed in a vector as a parameter into a function. It's the same exact concept if you're trying to do something like this within a function, right? If I'm trying to reference this vector, but I'm not creating a const reference, then I am making a copy of it. Example from the Tetris game, we have this tiles vector that we're creating, and we're copying this cells at a particular rotation state into here. We're making a brand new vector here, allocating memory, copying all of the elements into here for what? Just to iterate through them and then push back these new positions into another vector, right? So there's no reason why this has to be copied. This should just be a const reference if you want to use tiles as an alias. Now the next thing is, do you know how many elements you're planning to have in that vector? This doesn't even have to be an exact amount. It might be like some kind of maximum estimate, because the way that vectors work with their resizing is somewhat annoying. Every compiler has their own C++ library, basically, right? So GCC has their own, Clang has their own, and MSVC, Visual Studio, that's what we're using here, they have their own implementation, basically, of the C++ standard library. In MSVC, what happens is that every time you try and push back an element into a vector and you don't have the capacity for it, right? So initially, when we create this vector, we actually have the ability to store 0 elements. Surprise. When we push back the first one, it's like, I need to grow, I need to resize. So what does it do? Well, in the case of the first element that we push back, it just makes the size 1. But if we go beyond that, it will grow by 50%. So if you have 2 elements, you'll get 3, or rather room for 3. If you have 10, you'll suddenly grow to 15. Clang, I think, also does the same thing, and GCC will just double the size. So obviously doubling is good in the sense that you'll have fewer allocations if you're just iterating through a list like this, and you're just repeatedly adding elements, at the expense of potentially over allocating memory. And actually we can see this in action with our breakpoint. So over here, you can see we're trying to push back an element, and then where do we go? Into Emplace 1, add back, and if we just go up the call stack, we'll see the allocation over here, but right before that, we have a new capacity variable, which comes from calculate growth. And if we take a look at that, what does it do? It's got this geometric variable over here, which is old capacity plus old capacity divided by 2, right? So we're adding 50%, and that determines our new capacity. So what that means is that the capacity of this vector goes from 0 to 1, that's 1 allocation when we add the first element. Then from 0 to, well, you can't have 1.5, so 2, so that's 2 allocations when we add the second element. Then from 2 to, well, 2 plus 50% is 3, to 3 when we have 3 elements. Then from 3 to 1.5, I guess rounded up to 5, right? So basically to add these 5 elements, we need 4 allocations of memory. So just set the size first, and then do your pushback. And that's really easy to do. You just need to call this function called reserve 5. That's it. What that does is it says, I want enough space for 5 elements now. And so if we run our program with that, well, that was a bit easy. Now we're down to 1 allocation. Now, alternatively, what you can do is you can actually set the size over here in the vector constructor. That's the same thing as calling the resize function. So what's the difference between reserve and resize? Well, reserve will just reserve that memory for you. So it will just basically change the capacity of the vector to be 5. So not the amount of elements currently in there, but just the capacity. But resize will actually set the number of elements inside vector to 5. So basically that means that we now have 5 instances of the data struct inside this vector, just constructed with the default constructor. And so if we try and do this code now, we'll be pushing in 5 more. So we'll have a total of 10. So in this case, we actually have to go into our original code and change it to just be this. We're setting each element to this now instead of adding a new element. And that gives us the same result. So over here in our Tetris example, our real world example, over here with moved tiles, which we end up pushing back into, we would just either set tiles.size as the actual parameter over here in the constructor if we wanted to resize, or just reserve this amount because tiles.size is going to be how many we need. I think it's just 4 in this case. But of course, you could argue that there's no reason for us to actually default construct a whole bunch of these data struct instances only to override them. So I would probably prefer using the reserve function in this case. So that's it, one allocation. Are we done? No, because there's actually something else going on here, and that's one of the reasons why I decided to use a struct instead of just a primitive type, and that is copying. Copying this stuff. We have been concerned with just allocations thus far, but what we should also be concerned with is copies. So at the moment, data doesn't actually have a copy constructor. So let's add a copy constructor to data, and I'm going to print out this copied text over here, maybe copied data, and then we'll also have a copy count, which I will increment. So let's have a look at our copy count. Now I do want to mention that in this case, data is a very simple struct. We just have an integer. It's stored like in the actual struct memory itself. That's the only thing we're storing. It could be something that perhaps stores a vector of its own, and a vector contains a heap allocated block of memory, meaning that if we copy this data struct instance, we're actually causing an allocation because we need to copy that vector into a new one as well. So we're trying to avoid this. We're trying to minimize the amount of copies that we need to make. So let's have a look thus far how many we actually have. And you can see we still have 5 copies. Now, it's better than what it was. If we get rid of reserve, we have 15 copies. And if we get rid of our const reference in the print vector function, we have a sickening 20 copies. So we have made some improvement. However, wouldn't it be good if it was like, well, I don't know, 0? Is 0 too much to ask for? So let's put back our const reference, and then over here, I'm gonna bring back our reserve, which brings us back down to 5 copies. And so the first step here is to figure out where our copies are coming from. And for that, you can do the same thing that we did with this allocation function over here. And that is by just sticking a breakpoint into this copy constructor. Make sure you're running in debug, by the way. And over here, you can see that it's coming from this line over here. And the reason why is because we're actually constructing this instance of the data struct here in this stack frame, in this scope, and then we're copying it back into the vector, right? So this is really similar to what's happening over here inside Tetris as well. It's just, it's spread out onto 2 lines. We're first creating the struct instance over here, and then we're pushing it back into the vector, thus obviously copying it from here into the vector. It just looks a little bit more sneaky when it's done like this without an actual variable, an L value being created. And that's why we use a different function called Emplace back. And what Emplace back does is it lets you specify the parameters of the constructor. So instead of giving this vector the actual data object, we just give it the parameters of the object we want to construct, and it will do the construction for us inside its own memory. So we'll get rid of data, and if we had more parameters, we just specify them like this, and it will just forward them along and construct that data instance already in place, in its kind of final memory. Now you can also do this. Why? Because we have copy constructors, and copy constructors take in the very object that we are, right? Because we're copying from another object. So therefore, this actually still works. You can see I can go from pushback to Emplace back with no real change, but the magic obviously comes from actually forwarding along those constructor arguments. And so if I run this, 0 copies, 1 allocation and 0 copies. That's the dream. Now I would be a little bit sneaky here if I didn't actually talk about moving rather than copying, because whilst all we can see here, if we revert our code, so we're back to pushback here, all we can see here is that writing code like this causes a copy, and that's bad. And the reason why this is happening is because our data struct doesn't have a move constructor. If we add a move constructor, so I'll just copy the copy constructor, haha, take that. And then I will add in a move constructor. Let's go ahead and also add a move count. In this case, it's not gonna matter. There's not gonna be a difference between the copy constructor and the move constructor, but obviously if we had, say, a vector or something like heap memory, like a pointer to heap memory, then we would just take the actual pointer rather than copying all the elements, because we're not creating a new fresh copy, we're just moving kind of from one place to another, which is obviously much faster. If you don't know anything about moving in C++, move move semantics, that kind of stuff, this scary looking R value reference, then I have a couple of videos in my C++ series about that. So I'll have them linked up there. So we'll do moved data instead, and then we will print that out. So in that case, if we actually take a look at this, you can see we do a bunch of moved data instead, and we have 0 copies, but 5 moves. So yes, moving is much better than copying. It's not technically, I guess, available on every class because you actually have to add it yourself. Obviously, the standard template library will have that sorted for things like strings that you might want to move instead of copy. However, you know what's even better than 5 moves? 0 moves. And so the way you do that is, again, by using Emplace back, which will construct the object in place, which you should always prefer to do, and you get 1 allocation, 0 copies, 0 moves, and that, ladies and gentlemen, is the dream. So in summary, step 1, do you need to use an std vector? If you can use an std array, which actually, now that I think about it, we've ignored step 1 here, because in this case, we absolutely don't need a vector. So let me show you how to change this into an array. This would just be array 5, none of this, and then instead of Emplace back, we would just do kind of the same thing we did with the vector resize, where we just set the element to data I like that, and we're done. Now this gives us an error in this case because I actually need to add that operator, but just ignore that. So this is really step 1, because guess what? This isn't gonna be 1 allocation, it's gonna be 0 allocations, because they're just gonna be stack allocations, not heap allocations, which is an even better dream than what we had before. So step 1, do you need to use an std vector? If not, don't use it. Step 2, do you know roughly at least how many elements you're actually gonna have in that vector up front before you start adding them? One thing I didn't mention here, by the way, is the fact that you can do this kind of in increments, right? So if you know you need 1,000 for this and you might need 1,000 later, you don't have to do 2,000 at once. You can just do 1,000 and then increase that, like double it yourself basically, because maybe the 1.5 times the 50% that MSVC is adding is gonna make it so that you have to do like 2 or 3 extra allocations instead of just 1 if you actually know how much it's going to increase by. So basically try and manage the size, the capacity yourself by either allocating up front, by calling the reserve or the resize function, or creating the vector with the size in the constructor like this, or by doing that later on in your program. And step 3, avoid copies, avoid moves, use Emplace back. Don't use pushback like ever. I don't really think there's a huge reason to use pushback at all. I think just replace pushback with Emplace back, which again, you still need to use properly, meaning if this Emplace back was data like this, like it was for pushback, then that would function the exact same way as pushback. So you still need to make sure you're actually forwarding those arguments along like that. And that will make sure that you avoid copies and moves and just construct the object in place. Which, by the way, copies obviously can contribute to allocations, because if you're copying an object that has heap allocated memory inside it, it's gonna have to allocate more memory for the new copy. So hopefully this is a nice little guide to all of you. If I missed anything, let me know in the comment section below. I could have probably mentioned that if you're creating a new vector within a function and trying to return that, how that plays along with like return value optimization. There's some other things we could discuss, but I think in general, this is a decently comprehensive guide on how everyone should be using std vector, at least compared to what I've been seeing with all the code that people have been sending me. If you guys enjoyed this video, then please hit the like button and let me know in the comment section below. Do you want to see more of this? Let me know what you think I should cover next, and I'll see you next time. Goodbye.